Hello, today I'll be doing problem number 1. That is to derive Bernoulli's equation from the rate energy balance equation. So over here I've written down a couple things. The first one is I've written down the rate energy balance equation with this right here. And before we start deriving Bernoulli's equation, we need to make certain assumptions and as well as understand the characteristics of what define Bernoulli's principle. So one of the first thing, the core principles of Bernoulli's is that the flow has to be steady. Essentially what that means is that property does not change with time. So energy or let's say pressure does not change with time, and the flow is incompressible. That means that the density is constant throughout the flow. And in the problem, it's stated to neglect heat loss, so we already have that. And another assumption we need to make that there are no chemical reactions within Bernoulli. So that means the enthalpy between the 2 points that Bernoulli is measuring between the 2 points, or the enthalpy basically of the flow, there will be no chemical reactions. So then the change in enthalpy equals 0. And it needs to obey the conservation of mass or the continuity equation. So that means that the mass flow rate in is equal to the mass flow rate out, and that so that means the change in mass flow rate is just equal to 0. And from that we can start simplifying our equation a little bit. So with the first assumption that this has to be steady flow, that means the dt is equal to 0. And the second, with the third assumption that to neglect heat loss, and q dot is equal to 0. And we make the assumption that there will be no chemical reactions. So that means the enthalpy terms will go to 0. And from that, we could simplify the equations a little bit. I'll be moving the work to the left side. So we have work dot is equal to summation of m dot 1 as in the inlet, or v squared 1 over 2g plus gz1 minus summation of m dot 2 v squared over 2g plus gz2. So a couple things we can simplify, we can further simplify this equation because the summation part of the equation is written to accounted for multiple inlets and outlets. But Bernoulli's, we're just mostly dealing with a pipe flow. So just a pipe flow, one inlet and one outlet. So it measures velocity or the mass flow rate. So usually there's only one inlet and one outlet. So we can further simplify. We take out the summation part. So we have work dot is equal to m dot. And another thing that we can do is that the mass flow rate, the inlet and the outlet is the same, so we can just take out the subscript. So we just call it m dot v squared 1 over 2g plus gz1 minus m dot v squared 2 over 2g plus gz2. So, and then we can distribute the m dot into here. So we have work dot equal to m dot v squared 1 over 2g plus m dot gz1 minus m dot v squared 2 over 2g minus m dot gz2. And work dot is just work over time, and m dot is just the mass flow rate, over time. So we can multiply the time into all these to simplify it even further. So we'll have work is equal to the mass v squared 1 over 2g plus m dot gz1. This should not be m dot. It should be m minus m v squared over 2 over 2g. This should not be m dot. Minus m gz2. Yes, these are just regular m, just regular mass. And so a couple things that we can go from here is that so work is defined as pressure PdV, or VDP, and we'll be using VDP because we're interested in finding the different pressures, because that's what Bernoulli's equation is, finding the pressure difference between 2 points of a flow. And also if we look back into our assumptions that we have, so the density is equal to mass over volume, so the volume will be density, so the volume would just be mass over density. So we make the assumption that the it's an incompressible flow for Bernoulli, so that means that the density will stay the same, and as well as the conservation of mass, so the mass and the mass has to stay the same, so that means the volume has to stay the same as well. So which is why we will be using this expression for work, because yeah. And we can rewrite as V dP is equal to m v squared 1 over 2g plus m gz1 minus m v squared 2 over 2g minus m gz2. And obviously you could divide it by v over here, and then we'll just rewrite m over v as, you know, our density term right here. And dP is just pressure 2 minus pressure 1 is equal to, so we'll replace this with density, so density v squared 1 over 2g plus density gz1 minus density v squared 2 over 2g minus density gz2. And you just move the two terms, the outlet terms over here and the inlets term over here. So after we rearrange, we have P2 plus 1/2 rho v squared 2 plus rho gz2 equal to rho 1 plus 1/2 rho v squared plus rho g, this should be 1, gz1. Or yeah, so this is the Bernoulli equations that we familiar with. Or we can simplify it as P2 over gamma, which is a specific gravity. Gamma is just rho and g, plus this one you would have v squared over 2. Yeah, we don't need to simplify, but yeah, this is the Bernoulli equations that we have arrived at, and we have derived that from the rate energy balance equation. Yeah, and here is proof that me, Chandara Heng, did the video, and thank you for watching.